Alright, and this is going to be one of our last videos for this section on arc length and curvature. Here we're actually going to go through and compute curvature, which we saw in a previous video was given by kappa of t is equal to the derivative of the unit tangent vector per arc length unit. And so we can maybe compute that directly. Could be fun. But if we use the chain rule, I think it ends up being a little bit easier for us. So if I look at, oops, let's get that out of the way. If I take the unit tangent vector and I take a time derivative of that, okay, what I can actually do is break this down and say that this is the derivative of the unit tangent vector per arc length unit and the arc length function per time unit. Okay, that's implicit differentiation, so it's just saying that we can think of it as the derivative of the composition, right? So we can take the unit tangent vector composed with the arc length function. Okay, and so if I want to find an expression for the derivative of the unit tangent vector with respect to arc length, then I just have to isolate this, and wha-bam, I get derivative of unit tangent vector with respect to arc length is the derivative of the unit tangent vector with respect to time. I want to actually write this a little differently. Divided by the derivative of the arc length function per unit of time. Okay. Now, I previously said that we might need to pay attention to that s prime, right? S prime of t, and saying that that was the length of the parameterization vector that we have. So this really can be written as derivative of the unit tangent vector with respect to time over the length of vector x prime of t. Okay, and so that's really nice. So what I can say then is to get curvature, and I'm going to do kappa of t. This is given by the length of dt ds, okay, which we said from above, this is the length of dt dt per ds dt, okay, and then lo and behold, I can write this as, let's see, dt derivative of the unit tangent vector per unit of time over length of x prime of t, and I forgot another length symbol here. Doesn't much matter, because at the end of the day what I can say is that to compute curvature, I take the length of the derivative of the unit tangent vector over, and then a double magnitude here doesn't really mean anything, so we just say that's the length of the parameterization vector. The length of the derivative of the parameterization vector. Okay, and this is going to be much easier to use in practice. Okay, so now if we go ahead and use that formula, we can use this to compute the curvature of the example below. Okay, and then just an important note before we do that, the vector t is a unit vector, but t prime doesn't need to be, so just be aware of that, okay, if you're finding that the length isn't one. Okay, so curvature of a circle of radius a. Okay, I'll let you visualize that if you want, but what we end up with here is we can use the parameterization x of t as a cosine t, a sine t, and then t is within 0 to 2 pi. Okay, we can use that parameterization. So then I need vector x prime of t eventually, and so that's going to be negative a sine t, comma a cosine t. Okay, and I will need the length of it eventually, so let's just get that length here as well. Let's see, I think I just end up with a. Yeah. All right, and then the next thing, so I have the length, that's going to be the denominator in that curvature calculation, but I also need the unit tangent vector, right? And so this was defined as vector x prime divided by the length of vector x prime. Okay, and so if I do that, I end up with, okay, so I have these from above, right? And I divide that, both those by a, so I end up with negative sine t cosine t. Okay, and then I compute t prime. All right, and that's going to be negative cosine of t, comma, negative sine of t. Okay, and then per the calculation for curvature, I also need length of t prime, which is just 1. So then, finally, with all this, I get kappa of t is defined as the length of the derivative of the unit tangent vector over the length of vector x prime, and we said the numerator was 1 and a, so that's the curvature. Okay. Coincidentally, notice how that we had a radius a and we had a curvature of 1 over a. That's kind of interesting, okay? Because that actually leads us into the geometric interpretation of curvature. So if I have a given parameterization, the value r is equal to 1 over kappa is the radius of a circle that best fits the graph at time t, okay? And so if I have a curve like so, and I have a time x of t on here, then what I can do is I can take a circle and I'll make it variable lengths and move it around. And so I can make a circle that can touch that curve at that point, and probably most of the other parts of the curve. Let's see if I can make this just a little bit better. That's maybe good. Okay. So that's the circle that we're talking about, and this is actually called an osculating circle. Okay, and so we get a circle. The 1 over the curvature is the radius of that oscillating circle. If I have a curve that isn't as curvy, okay, so let's make it a little bit more like this, and I take a point here, x of t, and I have another circle. This circle could be actually quite large, and I don't know if I'm going to draw it right here, but I'm going to try to get it started. But that might be the circle. So this is going to be our osculating circle here. Okay, and so I'm going to have you just pause for a moment with these next two questions. So if we have varying sizes of oscillating circles, what does that mean about curvature and curviness? So pause and see if you can answer these on your own. In the first one, if we have a large oscillating circle, that should mean that the graph is actually not curvy. Because the curvature, so if we have a large radius, that means the curvature is really small. Okay. Conversely, if we have a small oscillating circle, that means the radius is small, meaning the curvature is high, so we have that it is curvy. Okay. In the next video, Dr. Agnes actually does some more computer examples with curvature and these oscillating circles. It's kind of an interesting thing to watch, and then that video will actually conclude this week's videos for arc length and curvature.